Imagine you're a structural engineer. You have spent 20 years designing buildings, calculating load tolerances, managing construction crews with access to cranes, concrete mixers, laser-guided surveying equipment, and every other tool that modern civil engineering has produced. You understand, better than almost anyone alive, what it takes to move large amounts of stone precisely and efficiently. And then, someone shows you the Great Pyramid of Giza and asks you a simple question. Could you build it today? Not could humanity build it. Could you, with a modern construction company, with modern equipment, with an unlimited budget and the best engineers and project managers on Earth, reproduce what was built on the Giza Plateau 4,500 years ago, to the same specifications, to the same tolerances, with the same precision? And the honest answer, the answer that structural engineers and archaeologists and historians give when they are being genuinely honest rather than professionally cautious, is that nobody is entirely sure. Not because we lack the technology, not because we lack the manpower or the resources, but because some of what was achieved at Giza and at a handful of other sites scattered across the ancient world was achieved with a precision so extraordinary and at a scale so staggering that reproducing it today would push the limits of what modern construction is capable of. And nobody has a fully satisfying explanation for how people working with copper tools and wooden sledges managed it first. This is not a fringe theory. This is not conspiracy thinking. This is what the engineering data actually shows when you look at it carefully enough. And the Great Pyramid is only the beginning. Let us start with the numbers, because the numbers are where the story becomes genuinely difficult to explain. The Great Pyramid of Giza was built approximately 4,500 years ago, during the reign of the pharaoh Khufu, and it remained the tallest structure on Earth for nearly 4,000 years, until the completion of Lincoln Cathedral in England in 1311 AD. It contains approximately 2.3 million stone blocks, each weighing between 2 and 80 tons, assembled into a structure that covers 13 acres of ground, and originally stood 146 meters tall. These are the facts that everyone knows. Here are the facts that are less well known. The base of the Great Pyramid is level to within just 2.1 centimeters across its entire 230-meter length, a flatness so precise that modern engineers using laser-guided equipment would be proud to achieve it. The four sides of the base are oriented to true north, south, east, and west, with an accuracy of 0.05 degrees, an alignment so precise that it was not surpassed by any human construction until the 20th century. The original outer casing stones, most of which were stripped away in the medieval period to build Cairo, were fitted together with joints so tight that a piece of paper cannot be inserted between them. Gaps of less than 0.5 millimeter across surfaces of polished limestone weighing tons. 0.5 millimeter across surfaces weighing tons, fitted together 4,500 years ago. Modern stonemasons who have attempted to replicate this level of precision using modern tools have described it as extraordinarily difficult, requiring multiple passes, careful measurement, and equipment that did not exist in 2500 BC. The standard explanation that Egyptian workers used copper chisels, wooden mallets, and sand as an abrasive, does not fully account for how this level of surface finish was achieved across millions of square feet of stone. Egyptologists acknowledge the precision. They do not all agree on exactly how it was achieved. But here is what you're about to discover. And this is the part that makes the pyramid look almost straightforward by comparison. There are other sites around the world where the precision is even more inexplicable, the scale even more staggering, and the conventional explanations even less satisfying. Sites where the stones are not just heavy, they are impossibly heavy. Where the joints are not just tight, they are interlocking in 3 dimensions in ways that would challenge a modern CNC machine. Where the structures have survived earthquakes that destroyed everything built around them, because they were engineered with a sophistication that we are only now beginning to understand. 12,000 feet above sea level in the Andes Mountains of Peru, on the outskirts of the city that was once the capital of the Inca Empire, there is a fortress called Sacsayhuaman. It was built by the Inca sometime in the 15th century, using stones that make the blocks of the Great Pyramid look modest by comparison. The largest stones at Sacsayhuaman weigh an estimated 360 tons, roughly the weight of 3 fully loaded Boeing 747 aircraft. They were quarried from a site more than 20 kilometers away, transported across mountainous terrain at high altitude, and fitted together in interlocking 3-dimensional polygonal joints, so precise that the walls have survived every major earthquake to hit the region for 500 years, including earthquakes that leveled the Spanish colonial buildings constructed around them using mortar and conventional masonry. The Spanish buildings fell. The Inca walls did not move. The joints at Sacsayhuaman are not simple flat surfaces fitted against each other. They are complex, irregular polygonal shapes. Some stones have more than 12 distinct faces, each fitted precisely against the corresponding faces of the stones around them in 3 dimensions. The stones fit together so perfectly that the walls flex and settle during earthquakes, rather than cracking, redistributing seismic stress through the interlocking geometry, rather than resisting it rigidly. This is, in principle, exactly what modern earthquake-resistant engineering tries to achieve, and modern engineers use computers to calculate it. How the Inca calculated it, how they even measured and cut these complex 3-dimensional surfaces without metal tools, without the wheel, without written mathematics as we understand it, remains genuinely, seriously, professionally debated. The standard explanation involves teams of workers using stone tools and a trial and error fitting process, gradually grinding surfaces together until they matched. Engineers who have looked at the geometry closely point out that this process, applied to stones of this size and complexity, would have taken longer than the historical record suggests the entire construction took. The math does not quite work, and nobody has a better answer. But if Sacsayhuaman challenges conventional explanations, there is another site in South America that goes further still. In Bolivia, at an altitude of nearly 13,000 feet, on the Bolivian Altiplano, lie the ruins of a site called Pumapunku, part of the larger Tiwanaku complex that was built by a civilization that predates the Inca by more than 1,000 years. At Pumapunku, the stones are not just large and precisely fitted. They are machined. That word, machined, is chosen carefully because it is the word that engineers and stonemasons use when they examine the stones of Pumapunku closely. The surfaces are flat to tolerances that require measurement instruments to detect variations. The angles are true right angles. The drill holes, and there are drill holes, perfectly circular, perfectly consistent in diameter, are bored through stone at angles that would require a drill press to replicate today. The H blocks, the most famous stones at the site, are identical to each other in their complex geometry, as if produced from a template or a mold, despite being cut from solid andesite, one of the hardest stones on Earth. Andesite has a hardness rating of around 7 on the Mohs scale, the hardest tools available to the Tiwanaku civilization, according to conventional archaeology, were made of bronze, which has a hardness of around 3 to 4. You cannot cut a harder material with a softer tool. This is not a matter of debate, it is basic materials science. And yet the stones of Pumapunku were cut, drilled, and finished to extraordinary tolerances using tools that, by the conventional account, should not have been able to do it. Mainstream archaeology offers several responses to this. The Tiwanaku may have had access to harder stone tools than are currently in the archaeological record. They may have used techniques, abrasion, percussion, controlled fracturing, that could achieve more than the simple hardness comparison suggests. And the tolerances, while impressive, may not be quite as precise as the most enthusiastic accounts suggest. Once you account for thousands of years of weathering and movement. These are reasonable points, but they are not the same as a complete explanation, and Pumapunku is not alone. In Lebanon, in the Bekaa Valley, at a site called Baalbek, there are stones in the foundation of a Roman temple complex that were not put there by the Romans. They were already there when the Romans arrived, and the Romans, who were the greatest builders of the ancient world, simply built on top of them because they could not move them and did not need to. These stones, known as the Trilithon, are among the largest worked stones ever moved by human beings. The largest, the stone of the pregnant woman, weighs approximately 1,650 tons. It is still lying in the quarry where it was cut, never successfully moved, as if even whoever built Baalbek eventually gave up on it. 1,650 tons. The largest crane currently operating in the world has a maximum lifting capacity of around 5,000 tons, but it requires a prepared foundation, precise rigging, and months of setup. The stones that were successfully moved at Baalbek, weighing up to 800 tons each, were lifted, transported, and placed with a precision that leaves no room for error. How this was done remains officially unknown. And then there are the Moai of Easter Island, the enormous stone heads, some weighing 75 tons, carved from volcanic rock and transported across the island to their platforms using methods that the islanders themselves, when asked by European explorers, described only as the statues walked. Modern researchers have proposed various mechanisms, rocking, rolling, dragging on sledges, and demonstrated that some of them are plausible for some of the statues. None of the proposed methods fully accounts for all of the Moai, at all of their locations, within the timeframes the archaeological record suggests. Across the ancient world, on every continent, human beings built things that they should not have been able to build. And the conventional explanations, ramps, sledges, thousands of workers, generations of accumulated skill, are not wrong exactly. They are just incomplete. Here is what is genuinely strange, and what mainstream archaeology has increasingly had to acknowledge in recent decades. The ancient world was not a collection of isolated civilizations, each independently stumbling toward the same solutions. The precision stonework at Pumapunku echoes the precision stonework of ancient Egypt. The polygonal interlocking masonry of Sacsayhuaman appears at sites in Turkey, in Greece, in Japan. The astronomical alignments built into the Great Pyramid appear, in different forms, at Stonehenge, at Angkor Wat, at Chichen Itza. The same solutions, the same techniques, the same impossible precision, appearing independently according to the conventional account, in cultures that had no contact with each other, separated by oceans and millennia. Either human beings, working independently across the ancient world, repeatedly arrived at the same extraordinary solutions to the same engineering problems, or there is something connecting these sites that we have not yet found, or there is something about what human beings were capable of in the ancient world that we have not yet understood. The honest answer, the answer that the engineering data and the archaeological record and the most careful researchers in this field will give you when they are being genuinely honest, is that we do not know. We know that these structures exist. We know what they are made of and roughly when they were built. We know with increasing precision, thanks to modern analytical tools, exactly how precise they are. And we know that our explanations for how they were built are, in several crucial respects, not yet complete. That is not a comfortable place for science to be. It is, however, an honest one. And in the gap between what we know and what we can explain, in the half-millimeter joints of the pyramid casing stones and the impossible drill holes of Pumapunku and the earthquake-proof walls of Sacsayhuaman, something is waiting to be understood. We built things we cannot explain, and we have not yet figured out how. Maybe that says more about the limits of our understanding than it does about the limits of theirs. The structures are still standing, the questions are still open, and every time someone claims to have finally explained how they were built, the engineering data finds another detail that the explanation does not quite cover. This channel exists for exactly those details, the ones that refuse to fit neatly into the story we thought we already knew. If that is the kind of history you want, stay here. The next mystery goes even deeper.